Hi, so welcome to part three of this series that I'm short series that I'm making, covering some of the themes in Andy Clark and Jakob Howey's books discussing predictive processing. In the last video, talked about prediction error, and prediction error being the difference between a model or predictive model and the data. And the idea is that in predictive processing is that one of the core mechanisms in predictive processing is that the brain is constantly trying to reduce prediction error wherever it can. And in doing so, it uses the prediction error to update models, predictive models that can make better inferences about the causes in the world. So in this video, we're going to be talking about the perceptual hierarchy, and this is sort of working out a bit more of the detail about how predictive processing might work in the brain. So what I've got is a sort of simplified hierarchy, which shows worldly cause. So let's just talk about the visual system, because it's the sort of paradigm case. Worldly cause could be sunlight hitting the photoreceptors in the retina. And then what we have here is this two-way flow. We've got prediction errors going up the hierarchy from low levels to higher areas, and then we have top-down predictions coming from high levels down to low levels. So what's happening is that at each level, let's say at the lowest level here, there's a top-down prediction predicting what that sensory input is going to look like. And then there's a prediction error unit, which we'll talk about later, which then says, well, there's a mismatch here between the predictions and the input, and the prediction error will then go up to the next level in the hierarchy. Same thing happens again in the middle area. Is the middle area, it's getting top-down predictions from the highest area. It's saying, is there a difference? Is there something wrong here? And then it's sending its prediction error up to the highest level. And each level then has to use this prediction error to change its models, to change its predictions that it's then going to send back down the hierarchy. So something to note here is that the fact that it's a hierarchy means that at each level it only needs to predict the input from the level below. It doesn't have to predict, the highest area doesn't have to predict the input from the lowest area directly. It's this layered approach. Okay, so what do we need to actually to do this on a sort of a neuroscience level? Well, we're going to need an expectation unit. So we're going to need something that can send top-down predictions about what it's expecting at lower levels of the hierarchy. And by doing this, it can suppress the signal that's coming from lower levels. And it's for the deep pyramidal cells might be able to play this role, although I think it's all sort of still being worked out exactly on a sort of cellular basis. But deep pyramidal cells might be a good candidate for this role as an expectation unit. Then we have its sort of opposite, if you like, the prediction error unit. This is something that's providing a feedback signal that informs the level above in the hierarchy. Hang on a sec, you haven't got things quite right. And it sends a message that there's a difference between the predictions from the level above and the input from below. And it's superficial pyramidal cells that are thought to play this role. So what does this actually look like? Like a true hierarchy, how it actually looks. It can get pretty complicated. This is a diagram from Carl Friston's work. Carl Friston is cited many times throughout both books. He seems to be one of the sort of pioneers in this area. As you can see, it can get a little bit complicated, so I've made a more realistic but still slightly abstract diagram to show how this might work in the visual system. So rather than saying the low and the high areas in the brain, I've labelled them. So we've got at the bottom the lateral geniculate in the thalamus. Then we've got going upwards, we've got the primary visual area, then the extrastriatal area, and at the top the parietal and frontal cortex. So in a real world system, let's try and think, how is this going to work? Well, the primary visual area is going to be sending down its predictions about what the sensory input is going to look like, and then in the lateral geniculate, it's going to be looking at those predictions, saying, is there something different, and then sending that prediction error up the hierarchy. So prediction error goes up the hierarchy, and top-down predictions go down, and those predictions are those expectations. Okay. So there's something else that kind of needs to be commented on that's really important, is that in the environment there's lots of, the signal noise ratio changes all the time. So sometimes there's a sensory input that's noisy and uncertain, such as when you're in sort of low light conditions or busy pubs or bustling restaurants with different smells and sounds and everything's going on. Based on contextual cues, the brain can actually, or within the predictive processing theory, it can make estimates about how precise the input is likely to be, and use neuromodulation to change the gain on prediction error units. So the brain can have a guess at how precise the information, how precise the signal is going to be, and then modulate how much gain to put on the prediction error units. So high precision expectations that there's going to be nice high precision data, will increase the gain on prediction error units. So high gain on the prediction error units will drive prediction errors up the hierarchy. In contrast, when there's low expectation for precision, the prediction error will not make its way to higher areas. And the consequence of this means that there's then a reliance. The top-down predictions are given, and